I'll give everyone a second to join us. Welcome everyone. You are joining us for optimization of LED illumination for hyperspectral imaging applications. This webinar is presented by Innovations in Optics and hosted by us at Photonics Media. Today, you'll hear from Dr. Thomas Brucolacchio, the CEO and CTO for Innovations in Optics. Thomas has been IOI's visionary, lighting the way forward for high technology solid state illuminators and systems. You will also hear from Christian Felseem, who leads business development and key account management for industrial machine vision at the Headwall Group. Today, Thomas and Christian will demonstrate how to optimize system throughput, sensitivity, and spectral accuracy by properly matching illumination performance to the capabilities of one's spectral imaging cameras. Before we get started, please know that you can ask questions or leave comments in the chat box at any time. If you have any technical problems during the event, please log out and rejoin us. You will be able to access the recording of this webinar online after we are finished, and you will get links to the recording in your email inbox. So with nothing further from me, I would like to welcome Dr. Thomas and Christian.
Hello, great to be with this webinar today.
Thank you, Haley. Okay. All right. Thank you for that introduction, Haley. We'll get right into outline. So brief introduction of both companies, and then Christian is going to give us a nice background, general background, hyperspectral imaging to provide perspective. And we'll talk a little bit about the specific focus of the webinar, attributes of a ideal system to give us some ideas how we should what we should think about as we design the system. But going into that design is an understanding of the LEDs, the camera system considerations, and then we'd like to talk a little bit about commercially available hyperspectral imaging illuminators, and do a little look at some metrics based on some optical modeling, and then introduce a new system, the Illuminate HSI, and then some comparison metrics followed by Q&A. Innovations in Optics was formed a little over 30 years ago. We have a strong IP with over 80 domestic US and international patents. We're located just north of Boston with a large facility that houses both the research and development and the manufacturing, where we do anywhere from low to mid volume to high volume manufacturing of primarily solid state illumination based on LEDs or pixels in some cases, or laser diodes as well. And now I will hand it over to introduction for Headwall to Christian. Thank you.
Yeah, thank you very much for having me today and inviting me for this webinar as well. And thank you very much for joining us today. Headwall actually is meanwhile a group of 5 companies. So Headwall was formed in 2003. We are headquartered just out of Boston, Massachusetts in the USA. And very close to us is Holographics, which joined us about 2.5 years ago. And in addition to that, we have 3 subsidiaries in Europe. Perglas in Delft, the Netherlands, making fantastic software for industrial use and analysis of hyperspectral imaging. InnoSpec and EVK brought hyperspectral imaging into industrial applications. And InnoSpec is based in Germany, EVK in Graz, and they help us also to serve our customer base in Europe. Now, overall, we provide everything that's needed to make the most of hyperspectral imaging. Started from its core, from optical components such as gratings and micro lenses or waveguides, as you can see here in the lower right of the corner. That's a specialty of holographics, and actually that forms business units by itself within Headwall, as we also provide these components to other hyperspectral imaging companies who very much value the quality of these components. So based on that, we have 2 units really providing hyperspectral imaging solutions. The one would be for remote sensing, where we serve applications in the agriculture and the environmental monitoring, or an example in the mining area. And here we provide everything that is needed, a complete package, including a drone, a hyperspectral imager, integration of other sensors like LiDAR, like IMUs, and or precision GPS, as well as a complete software package to analyze and integrate all these data. And then finally, industrial inspection, and that has been a lot of our focus in the past half year, or in the past years actually, where we approach sorting applications, grading applications by taking advantage of hyperspectral imaging. Now, what is hyperspectral imaging, and why is it being also called chemical fingerprint imaging? Now, a good way to get into hyperspectral imaging is comparing it to traditional imaging technologies like black and white image, which you certainly all know. So here in a black and white image, you get exactly one piece of information in every pixel of your image, and that's the amount of light or the intensity of the light. With an and that allows you to already identify where these objects you're imaging are in that picture. If you go to a color image, a classical RGB images, you already have 3 planes of information. So one plane reflecting the information in the red area, one plane of information reflecting the information in the green, and one in the blue bandwidth or blue domain. That already tells you a lot more about the image, and I will get back to that. Now imagine you are going from 3 to hundreds of planes of information. So you would have not only the information of 3 distinct bandwidths in a single pixel, but the complete spectral signature of your substrate in every single pixel. And this signature here, that is specific for the substance you are looking at. And that's why it's also being called the chemical fingerprint of your substance. Now, what does that tell you, or what can that tell you? Let's again make that comparison between black and white, RGB, and hyperspectral. A black and white image already gives you a lot of information, like the position of the substance. And let's imagine we would look at a bunch of apples here, its size, the number of apples you're looking at, as well as the shape. With an RGB image, you already get more information. Does that apple has like red cheeks? Is it ripe? Or is it already rotten? It's already getting brownish. Now imagine you're coming from that 3 planes of information to hundreds of planes of informations. That will give you much more information that you can analyze for analytical questions, like how ripe is it, the ripeness, or how sweet is an apple, estimating the Brix value, the acidity of the substrate you're looking at, especially of interest in fruits, or the firmness. Is that fruit still firm enough so I can ship it over long distance, let's say to another continent? Or is it so ripe that I need, and so soft that I need to get it to market as soon as possible and as close as possible? Or really looking at the object itself to identify whether it is the object of choice you want to produce, or whether this is a foreign object, and differentiation which is difficult to make with a simple RGB or black and white image. Now, how does hyperspectral imaging work? Well, there are multiple technologies. Let me introduce you to the one that has been mostly used in industrial applications, and that is the so-called push broom imager, where one line is collected, one line of your substrate, and that is that you're looking downward, an example, or imagine looking downward onto a conveyor belt, and then this conveyor belt is moved underneath the camera. So you are you're scanning your substrate line by line. Now this line of your substrate is being projected on the grating that diffracts the light, that differentiates the light by its wavelength content. So after the grating, that light is being reflected onto a sensor where we are getting a two-dimensional image. One dimension would be that spatial information. The other dimension, perpendicular to it, is now the spectral information in every single image. And then by screening that, by scanning your substrate line by line while you're moving the substrate under your imager, you are coming to what is being called this hyperspectral data cube with hundreds of pieces of information in every single pixel. But how do we make actionable information out of that in an industrial application? Well, in order to do that, we have machine learning-based analysis software like this is being developed by our daughter companies, Perclass or EVK. And this is essentially a two-step process, where in the first process, we are doing a classification. In example, a foreign object detection, differentiate between the substance of choice and anything that is not a substance of choice. Or defect identification. Are there any bruises on the apple? A typical defect. Or in a recycling application to differentiate between different types of plastics. Once we have classified, identified our objects, we can go one step further by doing a regression calculations, which would give us analytical information, such as moisture. How moisture is, let's say, a bread or a piece of meat. What toxins levels would I have in foods, an example, like histamine in fish, an example, or firmness or salt content in fish, or many other quantitative analysis measures which are having a signature in the spectral domain. So out of that, you're really getting actionable information. And the big advantage of this technology that is it's very, very fast. So it goes by the speed of light, actually. It is also very flexible because the amount of information you are getting through hyperspectral imaging is huge. And you can very quickly, just by changing your model of the analysis, adapt to new products, to new situations, to new inspection demands. And using this machine learning software, which is meanwhile available, it also has become very easy to apply and implement. Typical industrial solutions we are seeing and where we have done implementations, well, a lot of that would be in recycling, like you would here see in plastic recycling, but that is also in other recycling applications where hyperspectral imaging is used. Another big area would be in food analysis, food inspection, food grading. Like this is an application where we have analyzed the sweetness of oranges before these oranges are produced in an orange juice factory. Food safety, here I already mentioned measurement of histamine in fish, like here these would be a tuna fillet, or estimating aflatoxins in wheat. Another big area would be in food adulterations, like in herbs and spices. Other applications, and there are manifold where hyperspectral imaging are used, include electronic inspections, phenotyping to differentiate the quality of seeds, farmer, identifying an example as this image shows the distribution of the active ingredients. Here it would be ibuprofen in a tablet, color inspection, or many other process control applications. Okay, with this overview, where hyperspectral imaging provides value to many industrial installations, I would like to hand back to my colleague, Tom, to give you more details about what is really important for hyperspectral imaging illumination, and that is hyperspectral imaging, and that is the illumination. Tom, thank you.
Thank you, Christian. That's a wonderful introduction to HSI technology and really motivates the rest of the discussion. So as Christian mentioned, there are many applications for hyperspectral imaging. We're going to focus on a particular application that Christian also mentioned, that is looking at things like produce or plastics recycling, where the object size is on the order of many centimeters. We're also going to focus on the SWIR 900 to 1700 nanometer wavelength range, and to get a understanding of what attributes the illumination system could have, we would like to have high intensity across the full width of the line, large depth of illumination so we can see larger devices, materials and objects. We want to minimize specular reflections because that hides information. And we want a very stable and continuous spectrum without a lot of dips, because anywhere there's a dip in the wavelength, that's a lower signal noise ratio, which limits the line speed and your ability to resolve the metrics that you're looking for. The field of view of the camera and the illumination system ideally would be relatively close together, so that as you go out from the center to the edge of the field of view, the illumination of a given object would be similar, reducing shadow artifacts. It should have long life and low cost. So a little bit on the LEDs. So recently there have been developments of LEDs in wavelengths beyond 1,000 nanometers, and they've been around for quite some time, but improving every year. So in the 400 to 1,000 nanometer range, LEDs are generally much higher output than tungsten halogen lamps. So there are a number of very good systems out there in this spectral range. Again, we wanted to focus on the little more difficult 900 to 1700 range, and with recognition that LEDs go all the way out to about 2400 nanometers. But you can see the power drops off pretty sharply, so that out at these longer wavelengths, you would have to use multiple LED dye to get the intensity of those up. And here's a two different spectra for those two different regions, the 400 to 1,000 and 900 to 1,700. Notice that the scales are different. The output of the in the SWIR range of 900 to 1,700 is generally lower, and to get the output over in the longest wavelengths requires multiple LEDs, just because of the lower power to get the intensity up. But fortunately, that's mitigated somewhat by the responsivity of the detection systems. In this case, indium gallium arsenide is one of the typical material systems, and then for the shorter wavelength range, silicon. But you can see that the sensitivity increases with increasing wavelength. So that's fortunate because it mitigates some of the drop in these longer wavelengths, so you still get a good result and good sensitivity. So we need to think about the system level considerations for an illumination system. And if this blue rectangle here represents the camera, if the camera's closer in, then the angle going out to the edge of the field, so this is the dimension across the width of the conveyor belt, the long dimension of the line that the camera is looking at. And because the intensity fall off is a strong function of the cosine theta of that angle, generally it's better to use longer focal lengths where you can. And because you can see this, this is plotting the cosine of the fourth fall off for a shorter focal length. You see a drop towards the edge of the field. So that is also compounded by the fact that many non-telecentric C-mount lenses suffer from the intensity dropping as a function of field, which is called vignetting, compounding the issue. Additionally, many of the commercially available systems will fall off in intensity at the edge of the outer edge of the field, which is also working against you, because basically your sensitivity, the signal noise ratio at the lowest point, which is generally further off axis, is really what's going to limit the speed of the conveyor belt, because it's the signal noise ratio of the ability to detect um, at any point along the line that's important. So you don't know where the object's going to be. So so the lowest signal noise ratio is really going to dictate the speed of the line. Um, if you want to make it faster, then you need more light. The other way you can increase the signal noise ratio is by integrating longer, but because to get a doubling of the signal noise ratio requires 4 times the integration time, that's a big hit on the speed of the conveyor belt. So there's really no making up for having more light. And again, it's not just the light at the center of the field, it's the lowest illumination anywhere along the line that's really important in dictating that conveyor belt speed. So ideally, it would be a flatter distribution of intensity along the length of the line, or even increasing towards the outside to mitigate some of this fall off. The other thing worth mentioning is that the sensitivity also scales, or the signal noise ratio, optical power scales as 1 over the square of the f number. So using a lower f number lens is generally preferred, but it's always a trade-off, because the lower f number lenses are also more expensive. They're also more difficult to make, and they suffer from more aberrations and so forth. So there's always a trade-off to consider there. So the systems that we'll be looking at and describing are based on a slit width length, of 9.6 millimeters and a width of 30 microns, characterized by the head wall MVC NIR camera shown here. That covers the 900 to 1700 nanometer spectral range. For a 25 millimeter lens, you'd have about a 2.3 meter working distance. So we surveyed the landscape of HSI illumination and identified what we believe are the best commercially available systems. One is based on a modular cylindrical lens chip on board, where the system is modular in 100 millimeter increments. Another very good system has an integral off-axis ellipsoid reflector, so it's not modular, but it could be made in different lengths. And then we also wanted to look at another technology, the supercontinuum pulsed laser, which uses nonlinear effects at very high intensities at very short pulses to broaden the spectrum, which covers the range of 400 to about 2400 nanometers. Very interesting technology, but also extremely expensive. So in a cost-sensitive market, that won't work in all cases, or maybe few cases. We also look at the tungsten halogen lamp, a linear array of MR16 lamps, because that tungsten halogen has been a standard for a long time, and in the longer wavelengths still can work quite well. Real issue with it is that it doesn't last long, so there's a very high operational cost, and for continued calibration and replacement of lamps and so forth. That's where the solid state approach is very attractive, even though similar or higher startup cost, the operational cost of ownership is much lower. So we created some optical models based on these commercially available systems. They aren't necessarily exact representation of those products, but they're as close as we were able to determine based on our extensive optical design knowledge, and also kept the design in line with the data sheets that are provided by those systems. And we'll be modeling, as mentioned, a 900 millimeter field of view, and looking at a system that can operate, that is, have a field of view of the camera and the illumination coincident over a fairly large distance or length, so that we can look at large object sizes. And the model geometry, so if we have a conveyor belt going from left to right here, and this is represents the object, one approach is to have the camera at about 45 degrees to normal, and the illuminator as reasonably close as possible to keep a similar field of view. And this allows the specular reflections to go off away from the camera. For other applications like looking at pills and so forth, the typical geometry might be the camera looking straight down and plus or minus 45 degrees for the illumination, but that has a smaller depth of illumination. So for large object sizes, this is a good approach. And so we're looking at it in the optical models is the green represents the rays from the camera slit as projected onto the objects that are going by on the conveyor belt, and the black lines represent the illumination. So we're looking at the intensity distribution that's centered on nominally where they're aligned toward the center, and then as you go off, you can see that at some point the field of view of the illumination and the camera are not overlapping at all, so there would be no, so you couldn't look at objects over that larger range, but here we're looking at plus or minus 75 millimeters from the nominal. So the tighter the angle between these two, the larger the depth of illumination is going to be. So it's important when you're looking at a system to understand how large is it, how far, what is the working distance, how small an angle can I get for that system. So the first system that we were modeling is a modular cylindrical lensed line source. It comes in 100 millimeter increments per module. For a 900 millimeter wide line, there'd be about 12 or more of those devices required. This system has up to 12 adjustable wavelengths. And presumably you could adjust the intensity for each module to have higher intensities towards the outside, but they have a limit to the highest intensity, so that would be a fundamental limit. But it's a well-designed system. One nice attribute of it is that it's very low profile in this dimension, allowing tight angle between the illumination and the field of view of the camera. However, the intensity goes down quite a bit with distance. So in this case, this was a 200 millimeter working distance. So this represents the pseudo-color image of the intensity distribution at the working distance of 200 millimeters for this cylindrical modular LED line source. And you can see it's high uniformity across the line, relatively narrow width over the plus or minus 75 millimeter range. You start falling off a little bit, but it covers most of that range. And if you were to take these plots and plot them in the direction along the width and the length, you would get these distributions. So you see a fairly large range of intensities that results from objects that are either nearer or closer because of the angular extent of the illumination. You also notice that for 12 modules, if we're 900 millimeters plus or minus 450, we're starting to roll off at the edge of the field, which would be the fundamental limit to the signal noise ratio. So you may want to add some more modules, but during our in the middle of the area covered by the modules, the uniformity is very good, but it does change quite a bit in intensity with object position. So further positions would have lower intensity. So so at the bottom of a object going by, for example, the sensitivity would be a little bit lower. The second system we looked at is a contiguous off-axis ellipsoid reflector. So there would be right in this location here, facing down at the coincident with the first focus of this off-axis ellipsoid, and the light would go to the second focus. And this system is offered in up to 14 independent wavelengths. Now, where the first system we described has some control over the divergence owing by the micro lens array, this system here has no control over the divergence along the length of the line, which ultimately results in a drop in intensity as you move off axis, which requires a greater width of the system, which increases its system cost, of course. But you get a nice illuminated area along the line, but you can sort of see that it's dropping off with distance out to the 450 range, because the illumination is not quite symmetric at both sides of the on both sides, near and far of the working distance of 400 millimeters. You get a little bit different intensity distribution, and you're starting to fall off over this range, but it works over reasonably well over most of that range. And here you can see in the long dimension, getting out to the 450 range here, you're dropping off by a reasonable amount. So it's not the intensity at the center that's critical, it's the lowest intensity. So really the effective intensity would be down closer to 60, for example, down from 80 milliwatts per centimeter squared intensity at the center. The change in intensity with distance is a little bit tighter than the other system, which is generally good. And then the next system we were looking at is the sort of the old standard of tungsten halogen lamps, where you can see a parabolic reflector is used with the filament at the focus of the parabolic reflector. There's an array of 20 of them in this case, and added a elliptical 5x1 degree diffuser to make the intensity more uniform along the length of the line. That works quite well. It's a good system. Generally, these are made up of 20 watt. The system was designed of 20 watt MR16 tungsten halogen lamps at 3250 Kelvin. At that temperature, they last about a couple hundred hours. You could go to a lower color temperature to get longer life, but you also get lower intensity. So it's a trade-off, and because they have a relatively short life, it would require frequent recalibrations, which is also time that you're not using the conveyor belt. And when the lamps have to be replaced, that's downtime as well. So there's a high cost of ownership, not accounting for the cost of the lamps themselves or the technician time, but really the downtime of the line. The array of tungsten halogen lamps gives a nice, relatively uniform output, and you can see it works very well over this depth of illumination, primarily owing because the filament gives a fairly, as the magnification of the filament gives you a fairly wide line, which means it's going to work over a fairly large range of depths. But the intensity is relatively low compared to the first system we showed, which is a little more than twice this, and several times lower than the second system we showed. But otherwise, works quite well. The distribution is fairly tight as a function of distance. And then we wanted to mention the super continuum fiber laser, which is a very short pulse that is very high frequency. And so the result is what looks like a continuous spectrum in terms of the integration time of these systems. So there's many pulses over given integration time. So it looks continuous. It has output over the visible spectrum going out to about 2400 nanometers. So it's very good from that standpoint. Has a relatively high optical power, similar to what we'll show for a system we have later. But the real system, and it can be imaged relatively easy because it's a single mode fiber. The optics aren't complex. They can be put quite close to the pupil, the output of the camera. But its biggest drawback is that it's very expensive. So in most applications would not be viable because of the cost. Now we want to talk a little bit about a system that's being developed at Innovations in Optics. We call it the Lumi HSI LED illuminator. So essentially it's a patent pending projection of a line that's created either by the output of a tapered optic that's rectangular in the same aspect ratio as the field of view of the camera, or a fiber optic, in this case, a bundle. So fiber optic illuminator, round or square, goes to a line over here, which is imaged. So each module is imaged under the full width of the field of view of the camera. So you could use one or more modules. If you want to increase the intensity, boost the line speed, you just add more modules. But one module will suffice and give similar performance to the first system we talked about at a reduced cost. We're expecting that the fiber optic version would be out later this year, towards the end of the year, and early next year for the direct view system. The difference between the fiber optic and direct LED illumination is about 25 to 50%, and that's owing to the fact that the interstitial spaces between the optical fibers, which are on the order of 50 microns, represents a loss in intensity. You can fuse the bundles to get some of that back, but it's still not as good as direct illumination. But it offers nice modularity. These illuminators can be positioned elsewhere, so it's a space consideration as well. But the modules that have the LEDs directly in them can also be spaced the same way. So in terms of their imaging, they're very similar, just a little bit higher output with the direct type. So the illuminator itself, the fiber optic illuminator, is based on our Lumi Spectra, patented Lumi Spectra product. Has up to 14 independently controlled wavelengths, proprietary thermoelectric cooler for the purposes of achieving long life and stable spectrum. LEDs shift their wavelength, particularly in the longer wavelengths, as a function of temperature. So you need to keep the temperature of a system very stable. And the lifetime of an LED, kind of a rule of thumb, is for every 10 degrees increase in temperature, you decrease the lifetime by about a factor of 2. That varies from LED to LED, but that's a reasonable rule of thumb. So by keeping the junction temperature low, you can improve the lifetime and drive at higher currents at higher lifetimes. System has a proprietary GUI or Modbus control, Ethernet, USB serial interface, and can interface to fibers that are either round or square up to about 7.8 millimeters. And it has enhanced intensity or optical power due to our patented recycling technology that's built into it. Again, we're imaging coincident with the field of view of the camera. So the line would be a similar aspect ratio, and then it's imaged by the lens system, which is chromatically corrected and has no vignetting to give very high uniformity across the width of the line. So you can see over the full range, it's very uniform. You can see a little bit, the size is increasing as you would expect. The same would happen with the field of view of the camera. That's just the magnification effect. You see a tight distribution of intensities. Of course, since as you move further away, the line is getting longer. That means that the light is going to drop a little bit. But it's because of the angular extent, it's a very tight distribution. You also note that it's very flat response out to the edge of the field of view of the camera, which is also important. So again, it's the lowest signal noise that's going to dictate the line speed. So that's important. Has a relatively long working distance and tight angle between this is the actual camera with a 25 millimeter focal length image down into this area. So the other version of this system would be the direct LED system that has essentially the same lens, but the LEDs and a tapered optic that would have the same aspect ratio as the fibers are located in this box with a liquid cooling that is based on a system that we developed for our high power illuminators that are in the ultraviolet range for maskless lithography and 3D printing. So the same high performance, very low thermal impedance technology would be built into this system. And you can see power, Ethernet, USB here. So this is a comparison of the intensities over this range for the different technologies. This black line up here is a 3-module direct illumination Lumi HSI system. The green is, and this is on axis intensity. So you can see here, for example, this the cylindrical ellipsoid is relatively high in the center, but dropping off. So the green 3-module fiber HSI, Lumi HSI, is similar on axis, but much better. So achieves better signal noise ratio at the edge of the field. And just showing the information another way. So this is the tungsten lamp down here. The ellipsoid, cylindrical ellipsoid, relatively high on axis, but remember the effective is really lower because of the fall off the edge of the field. And then the first system we looked at, the modular cylindrical lens system, is relatively high compared to the tungsten lamp and similar to the single fiber optic version of the Lumi HSI in terms of its on-axis intensity. But of course, this has better through focus illumination stability. And again, if you want to use multiple modules, so for example, this is 12 modules with just 3 modules, we achieve very high intensity, which will improve your line speed considerably. So a nice option for the HSI community. We'd be happy to field any questions about that, and contact us with your interest. Another way of comparison matrix of the different technologies is looking at the intensity for, this is a Lumi HSI, and the modular cylindrical lens system, the ellipsoid, tungsten halogen, and the supercontinuum laser. So you'll note that the supercontinuum laser can have, well, if you had more modules of the Lumi HSI, of course, it'd go above the 100 if it's more than 3, but with 3 modules, still much lower cost than the supercontinuum laser, which is way up there. But these other sources are still higher in cost than for the same performance. So this higher end of the cost for the Lumi HSI is based on multiple modules, which would be up towards the higher end of this performance. So for similar performance to the cylindrical lensed version, the Lumi SI would be much more cost competitive. The solid state systems all have very good lifetime, generally greater than 10,000 hours. And again, the tungsten, very low lifetime, which means really high operating cost, which is not ideal. Noted here is the intensity along the length of the line. Of course, the Lumi HSI, as we mentioned, has excellent performance. It doesn't need to go to a larger width to get that. with the cylindrical lens system, if you had 9 modules instead of 12, there'd be significant roll off at the edge of the field, but it's very good for the longer length. Could be better if you added more modules, and then it'd be excellent. Cylindrical ellipsoid rolls off even for long length, so you'd have to go much longer to have no effective roll off. So that's, but it does have high output, so that can counter some of that roll off, but relatively high system cost. Tungsten is relatively low system cost, but again, that's the upfront cost. The operational costs are very high. So with that, I'd like to thank everybody, and please feel free to contact us. Note that we have a lot of other systems, our LumiBright illuminators here that are used in many medical and industrial applications, including UV curing. We have a solar simulator that came out recently that has world-leading performance in terms of its class A++, very high uniformity and very close performance to the sun with regard to the spectrum. We have a system that's just coming out, a multi-wavelength endoscope illuminator. We have other solar products that will measure the performance of photocells. This is a 3D printing UV illuminator, and this is a maskless lithography UV illuminator. You can see the liquid cooling technology on the back of this that would be implemented on the Lumi HSI, and this is a series of projections which either have very high uniformity without a reticle or using reticle along with commercially available C-mount lenses to get much higher output than by several fold than the nearest competitor, and gets around the speckle issue that you have with patterns with when lasers are used in imaging applications. So once again, thank you very much, and that concludes the talk portion, and now we can get into the Q&A. So I'll hand it back over to Haley.
All right. Thank you, Thomas and Christian, for presenting. We now have time to take a few questions before we close. If you have not already, please go ahead and type your questions and comments into the webinar chat. The first question is, how do you ensure spectral stability over time and temperature drift?
Okay, well, so that's a really critical point, because as Christian would tell you, the stability of the spectrum is really paramount, and in particular when you're talking about there is some structure with LEDs. So if you see those, if these move around on you, that's going to change the calibration of the system. So so those really can't be moved. So that really requires very tight control over the temperature of the LEDs. So with systems that are air cooled, you would have to elevate the temperature well above whatever the room's going to be, and then you could control the fan speed to control the temperature. The downside of that is that by elevating the temperature, you're reducing lifetime and output of the intensity. So the systems we were describing have either thermoelectric coolers, which can hold the temperature to within fractions of degrees C, or liquid cooling systems, which can hold the temperature quite close, on the order of a degree as well. So that keeps the wavelengths from shifting around, and also by reducing the temperature increases the lifetime of the system. Thank you for that question.
Great. Next question I have is, how important is uniformity? Is higher uniformity worth additional expense?
That's a good question, and it really depends on the situation, what you're looking at. And so if your intensity over the entire area, even if it's lower on the edge of the field, is sufficient for the line speed that you're looking at, then you don't necessarily have to invest in a system with higher intensity. But to really optimize performance over the full width of the line, noting that the signal noise ratio, therefore the sensitivity, is based on the lowest performing signal noise ratio that does say that it is critical to have high uniformity across the entire line to achieve the highest throughput. And of course, throughput is very important. Let's see, just have some noise on the line right now, and if someone got unmuted. Yeah, and so that's really a case-by-case basis, and it can also depend on what objects you're looking at, and whether they're wet or have specular reflection, or what the diffuse reflectivity is, what the colors are. So that can so depending on the spectral reflectivity, some objects can be very low, and so that is the illumination. If they're only reflecting 5% of the light, then you require higher illumination. So it really depends on what you're looking at, how fast you need to go. But in general, the better the uniformity, the better line speed you're going to have.
Yeah, I couldn't agree more to what Thomas said. It's that was the reason why in the past halogen illumination had been so popular for hyperspectral imaging, because they have a very uniform in the width as well as in the depth, a very uniform spectrum. But with LEDs, this has become more complex, so you really need to keep an eye on that. And that is also about when you analyze the data. If your analyze algorithms depend on where you measure and which depth or which width, then this costs you speed. And that's not what you want to have, definitely not.
Great, thank you. The next question I have is, what illumination geometry do you favor and why, for a specific application or range of object sizes?
Okay, Christian, I think you may be a good one to field that. But in general, as mentioned earlier, when you're looking at something of relatively small size, then different geometries can be used, and very typically it's a camera looking straight down, normal to the conveyor belt, 45-degree, maybe plus or minus on the illumination. Gives very good uniformity. The object size is small, so you don't need as great a depth of illumination. But if you're going to large object size, that's where you would go to a system like we described, where the light is coming in at a more like a 45-degree-ish angle. But we would encourage people to try different angles, because depending on what you're looking at, the best orientation can differ. So Christian, I'd like to hear your input on that as well.
Again, the depth of the measuring field is important. And when Tom says it's about the height of the object, already the height of an apple can make differences here, where you have a different spectral composition at the bottom of the conveyor belt compared to the top of the apple, at the height of the apple, or if you think about a fish or whatever goes over your line. So it's really important not only to have the same spectral composition across the line, which is already a challenge, but also in the depth of the field. If you really want to reach high analysis yields, it is achievable, but it's not that you can just use any type of illumination for that.
Yeah, that's a really good point, Christian. So the systems that we described that have larger variance over the range of the depth of illumination will suffer more in signal to noise for the object distances that have the lower intensity. So it's really important to have less variation over the depth. Okay, thank you.
Great. The last question I have here is, what is your preferred angle of the camera and the illumination relative to the normal to the conveyor belt, and why is that optimal for your application?
Okay. Again, for this specific application, roughly 45 degrees, but again, it depends on what you're looking at and what the reflective what the diffuse and specular reflection properties and colors of that object are. So you may want to vary that angle dependent on those factors. But in general, you want to keep the illumination, the angle between the illuminator and the camera relatively low, unless you're going to say normal incident or camera looking straight down, in which case you would suffer from more specular. So that's why you want to bring the angle away from the normal to direct the specular light. So if you're looking at things like poultry or meats and so forth, they have they have a lot of water content, and so you're going to get pretty high specular reflections. So systems like that, you want to redirect that specular reflection away from the camera. Christian, welcome your input as well.
Yeah, exactly. It certainly also always depends on the machine you are integrating your solution into. There might be spatial restrictions you have to work with, but any angle above, let's say, 15% would be preferred. That is not only true for objects which are wet, as Thomas made, but also which have a polished surface, like an example, metals, when you want to differentiate metals or analyze soldering points, then you don't want to have the specular reflections. And that's why it's a good idea to have some kind of an inclination.
Great. We do have one more question that came in. What is the difference between multi and hyperspectral imaging?
That's a good question. If you want to field it, Christian, that's fine. I mean, my perspective is that the hyperspectral camera has all wavelengths available, as Christian said, and for different types of objects, the best wavelengths are going to be different. So the hyperspectral system is more adaptable to different situations, but you might want to focus on particular wavelengths for a particular application. So, as Christian mentioned, they do a lot of signal processing, right? There's a lot that has to happen. So when that object goes by, you have to do something with it. You have to make a decision, and that has to happen fast. So for a particular application, there may be specific spectral regions that you're going to key in on, and maybe not look at all of the other wavelengths that are not really buying any information for that application. But if you had a system that was very, very one-dimensional and that you were always looking at the exact same thing, you could key in on specific wavelengths, both for the illumination and the detection that would work well for that application. But still having a broader spectrum is going to give you better sensitivity, because there's the spectral shape to consider as well that is characteristic of different materials. So, Christian?
The key point is really the flexibility and the accuracy of the analysis. In the past, the algorithms and also the computing power has often not been sufficient to really analyze all of that data. But meanwhile, that has improved a lot. So really, you can benefit from recording all this wavelength range, at least implement a hyperspectral camera, which offers, like I said, hundreds of wavelength bands compared to multispectral, which would be tenths of bandwidths. So you are having this flexibility in your machine, and which data you finally analyze, you can still adapt later on. But using hyperspectral imaging, you gain a lot of flexibility into your implementation. That's the big advantage.
Great. Thank you, Christian.
Thank you both. If we have not answered your question already, please look out for a reply from us via email later. If you think of another question for us, you can email webinar@photonics.com. I'd like to thank our presenters one last time, Dr. Thomas Brucolaccio and Christian Felseem. All of you for participating in optimization of LED illumination for hyperspectral imaging applications. This webinar is presented by Innovations in Optics and hosted by us at Photonics Media. Thank you all so much.
Thank you.
Thanks a lot.